Here we look at the airplane engine life expectancy example in Excel. According to the problem, an airplane engine manufacturer has learned through extensive flight tests that the life of their engines is normally distributed with a mean of 36,500 hours and a standard deviation of 5,000 hours. So the mean life is 36,500 and the standard deviation is 5,000 hours. Given that knowledge, the company is trying to answer a number of questions. For example, they want to calculate the percentage of the engines that are going to last more than 40,000 hours. So P of X larger than 40,000. So P of X, which is the life of the engine, being larger than 40,000 hours. But before trying to answer these questions, let us look at the problem more closely. We know that every given normal distribution is specified using its mean and its standard deviation. So we are going to use these two pieces of information to reverse engineer some fictitious or simulated engine lifetimes. So simulated engine life. I can use the function that you see here to generate numbers that are normally distributed with a mean of 36,500 and a standard deviation of 5,000. So norm I and V, and then the first parameter is rand, which is a randomly generated number between 0 and 1, uniformly distributed, comma, the mean, comma, the standard deviation. Note that generating these simulated numbers is not necessary for answering the question. We are just doing it for demonstration purposes. So my first simulated engine life is created and shown here. Now rather than having just one, I can go ahead and create, say, 10,000 simulated engine lives. For that purpose, all I need to do is to drag this for 10,000 rows. Here I have the 10,000 simulated engine lives created. Now note that in reality it works the other way around. So you go and look at 10,000 different engines, note their lives, and then based on that calculate a mean and a standard deviation. But here for demonstration purposes we are doing the reverse. I'm going to select the entire range and insert a histogram. You can already see that the histogram looks like a bell. Now the way Excel works is that if I double click here, it creates another set of 10,000 simulated values. So now you see a slightly different bell, and I can do it again and again, and you see that every time I get a slightly different bell, and that is of course because these numbers are generated randomly. I can right click here, go to Format Axes. The automatically selected bin width is currently at 820. I'm going to change it to something like 1000 so it's easier to understand. Now to stop these from constantly changing, I can go to Formula and then Calculation Options, and then temporarily switch this from automatic to manual. And these random numbers are going to stay the same, which makes our demonstration easier to understand. Now let's try to answer the first question. The question is asking about the probability of an engine living longer than 40,000 hours. So the answer to this question is this area to the right of the line divided by the entire area of the curve. The way Excel's function work is that it calculates the area to the left of the line relative to the entire area of the curve. So we need to take a preliminary step by calculating the probability that an engine lives less than 40,000 hours. That is equal to norm.dist of x. X in our case is the limit of 40,000 hours, comma, the mean of the distribution, comma, the standard deviation of this distribution, and comma, true because we are interested in calculating the area under the curve. So the area to the left of this line is 70% of the entire area of the curve. But again, remember that we are interested in the area to the right of this line. So to calculate that value, all I need to do is to subtract this value from 1. So 1 minus this value, which is 0.24 or 24%. And this is the answer to the problem. So 24% of the engines are on average going to last more than 40,000 hours. Now let's try to answer another question. The engine manufacturer is offering a replacement warranty for those engines that live too short. But the manufacturer doesn't want to replace more than 10% of the engines. So the question is to determine the place of this line such that 10% of the data falls to its left and 90% to its right. So we want to move the line such that the highlighted area is only 10% of the entire surface of the graph. So lifetime to make 10% of the engines eligible for replacement. For this purpose, I can use another function named norm.inv or norm inverse. The first parameter is the percentage, so we know 10%, so 0.10, comma, the mean, which is 36,500, comma, the standard deviation of 5,000. And the answer is roughly 30,000 hours. So if the company announces that it's going to replace those engines that live less than 30,000 hours, then it would end up replacing 10% of the engines in the long run. Finally, the company is interested in calculating the percentage of engines that live between 30,000 hours and 40,000 hours. So P of X being between 30,000 and 40,000. So we want to determine the percentage of engines that live between 30,000 hours and 40,000 hours. So we are basically interested in calculating the relative size of the area between the two lines to the entire size of the bell. And this involves two steps. First, calculating the area to the left of this line. Second, calculating the area to the left of this other line, and then subtracting them. So P of X less than 40,000 and P of X less than 30,000. So this one equals norm dot dist 40,000, comma, mean, comma, standard deviation, comma, true again. And this other one equals, similarly, norm dot dist 30,000 this time, comma, mean, comma, standard deviation, comma, true. So 75% is the proportion of the area to the left of this line, and 9% is the proportion of the area to the left of this other line. And to calculate the area in between, you simply subtract the two. So this equals this minus this other one, which is roughly 66%. So about 66% of the engines are going to live between 30,000 hours and 40,000 hours.